Good morning. Welcome to Mr. Render's class, room 101, period 4. We're looking at sampling distribution models.
Excellent. Thanks, Jalen. Let's do this. Okay, so what's going to be really weird about what we do this week is that we're going to be able to do a lot of stuff, say a lot of things, write a lot of sentences, but not actually do any real work. And I say that not because you're not going to do anything like with your hand and writing, but I say that because a lot of this stuff was discovered hundreds of years ago, and you actually don't need to run samples over and over again. Someone did for us, thank you, and what we realized is that if you do this, if you were to take samples out of populations and calculate proportions, and we'll do an example later today about cars that are speeding on the highway, you will find out that if you made a histogram of the proportions for all of your samples and plotted them as a histogram, it would be unimodal and symmetric. And we have a word for that in this class where we've seen things that are unimodal and symmetric. We ask ourselves, can we use what? Say it again? Okay. The normal model. That's what this week's going to be all about. Okay? We're going to use the normal model to make our sampling distribution models. Today will be for proportions. Okay? So proportions will be those percentages. And then tomorrow will be for means, or our averages. All right, so two kind of ways we're going to do this. Now, when we do this, anytime we talk about a model, we always have to have two parameters. Do you guys remember the parameters for a normal model? If I write it here, go away. If I write it here with that capital N and open a parentheses, does your brain know what needs to go in here? Mu and sigma, very good, right? Or winky owl face. No? I always think it kind of looks like an owl, somewhat. An owl. Yeah, go, woo, woo, like those things? Yeah. Now, you're going to see that if you look to the right of that owl, you'll see that we're using P, all right, which is the population proportion, all right, not what we used P for last unit. What was P for last unit? Probability of success. So it's different. So I need you to change your brain on that. I'll put that over here. P is the population proportion. Now, what's really interesting about this is we're going to do a problem where they tell us what P is. All right, so we have no problem finding our mean, which is that number, and then finding the standard deviation, which is this formula here. But we can also do this. This is what's crazy about this. We can also do this even if we don't know the population proportion. Even if we just do a sample and use that proportion, we can use that. That's called P hat. All right, so that's a symbol you'll start seeing from now until the end of this class. P hat is the sample proportion. You guys remember the symbol for hat? Yeah, looks like this. Yeah, P with a hat. That's called the sample proportion. So sample. That was a loud plane.
What does the N stand for?
Does anyone know what the N stands for? Say it again. The number of the sample size. Very good. And pretty much every problem, Yesenia, they're going to give you the sample size. We will do a problem next week and some weeks after where you will actually, and this is what pollsters do before they actually pick up the phone to call you to ask your thoughts about something. They actually have to figure out, based on some different variables, what sample they need to acquire. All right, so there is a scenario where I'll show you where we have to calculate the sample size, but that's a very unique scenario. Okay, let's keep going. Now, when we do this, and you're going to get so sick of this over the next 4 months, okay, so I'm very sorry, but you have to do this. Anytime we want to use a sampling distribution model, and today, again, we're going to use that for a proportion, we must make assumptions and check conditions. I want you to say that to yourself. Make assumptions and check conditions. Make assumptions and check conditions. It's like a mantra. You need to always say it. Like, I'm at a red light, make assumptions and check conditions. Right? I'm assuming people know that if their light is yellow, they should be slowing down to stop. But do I always do that? What conditions do I check? Before I go, I look to see if anybody's going to run the red light. Every day when I drive, I'm making assumptions, but checking conditions because I want to still be here. All right? I know that's a silly example, but that's something you do in your life that is statistics. You know people are supposed to obey traffic laws, but do you always assume that? No. That's why you have to check to be sure. Look both ways before you cross the street. Right? You didn't even know this, but when you were 4, you were already learning statistics. I tell that to my son every day. Look both ways, check those conditions. Do you guys think I do that?
Yeah.
See, it makes me happy that some of you do. He said he was like, nope. Okay. Oh, was he? Okay. All right, my bad. The independence assumption. It's exactly how it sounds. We need to make sure that whatever we're sampling, that when one thing happens, it doesn't affect the other thing. Now, I know that has no context. I'm sorry. It's not a problem. But when we do an example today, you'll be able to hear more what it looks like in a problem scenario. The sample size assumption is a great assumption. We have to assume that the sample is large enough. All right, so we're assuming that n, our sample size, is large enough. Now you might be asking, how do I know when it's large enough? Exactly, right? And that's where we're going to do a condition. We're going to check a condition that will make us feel better about saying this sample is large enough. All right? Questions so far? You're going to use these assumptions constantly. Okay. Now, here are the conditions, the corresponding conditions that we are going to actually check and write down something about. So we're always looking to see if they say something in the problem about randomization. Did they randomly sample? Because you know from being in this class, any sample that's not taken randomly could present some issues. All right, so we want to ask ourselves, did they randomly sample? We also want to ask ourselves to think about, is our sample larger than 10% of the population? We're hoping it's not. I've told you this in the past with like the M&Ms. You know, when you take out an M&M and put it to the side, do the probabilities change? Yes, they do. If I go to the M&M manufacturing place, right? It sounds like a magical place. Just imagining these big, massive stores of M&Ms. And I go in and I pull one out of millions of M&Ms and I put it to the side. All the probabilities change. But if it's millions of M&Ms, that change is so small that it's basically as if it didn't change. Okay, so that's this in a nutshell, the 10% condition. So we're going to check that to make sure that we think there are more than 10 times our sample size in the entire population of whatever it is we're talking about. The third thing, the third condition, the success and failure condition. You guys remember that one? You've already done that condition, right? You've already done this condition. So we're going to do this again, n times p, n times q. We're expecting to see 10 or more successes and failures. All right, and so I love this line right here. I call this the Goldilocks line here. Just right. Questions? So we're like only a minute or two away, I know, it's exciting, from making a sampling distribution model for a proportion. That's what we're about to do. All right. Now, if you end up having a sample, all right, the problem we're going to do is not a given sample to us. Say you have real data from a sample you've taken. Everything we have said up until now is still true. Everything is true. But I told you it's going to change, that you're going to use p hat as opposed to p. So anytime you see the letter p when you're using samples, it'll change to a p hat because it is a sample, not from a population. So that's all that's happening here on this slide, so that you know the difference when it's a sample and when it's a population. All right. Are we ready to try one? What I want you to do is I actually want you to flip. And I tried this out. I was hoping you guys would be happy about this. So if you flip to the second page, like the front of the second page, it should say examples of normal models for sample proportions. And what I did was I did less slides so they're bigger, so you have more room. All right? So let's go there. Should look like this. Okay? All right, let's see. Emmanuel, do you mind reading this for us? The two little sentences here.
Of all cars in interstate, 80% exceed the speed limit. What proportion of speeders might be sealed among the next 50 cars?
Okay, so the first thing I ask myself is this an actual sample? Did somebody go out to the highway with a radar gun and find 50 cars and measure their speed? Did someone do that? No. So this is not from an actual sample. They're telling us to assume that this 80% right here, is from a what? It's not from a sample, it's from a what? If it's not from a sample, it's from a what? You're going to say it, Sylvester. A population. This is a population. So when I think this is a population, I'm thinking 80% is what? It's from a population, and it's a percentage. So this is our P. We are assuming that the proportion of cars driving on the interstate, so the highways around Houston, 80% of them are speeding. For any of you that drive on the highways, that sounds about right. Now again, that assumes, let's not say that word because we're going to use that word later. That number, in my mind, when I think about myself, if I'm driving 62 and a 60, I'm speeding. Even if you know you're not going to get pulled over for that. All right, is everybody good? So you might be thinking, wow, that's really high. But if you think about how many people go 5 over the speed limit, technically you're speeding.
So it's not, so we use the hat whenever we
have a sample. If this had said they went out to the freeway and measured 50 cars and found that 80% of them were speeding, that would be P hat equals 0.8. Now we could still do all of this. If that was the case, we could still do it. We just had more hats. All right? So, before we actually draw any curves, do any numbers, do any calculations, we need to do what? Before that, make assumptions. Very good. So the first assumption you're going to make is the independence assumption. Let's make it right now. You should write this down. The independence assumption. What I tell students is I'm okay with abbreviations, just not that result in bad words. Okay? So you'll notice I'll never abbreviate assumption. All right. Just like I tell geometry students, when they ask about like the side angle side, all those different things, if it makes a bad word, it's not okay. So like, oh, what about the angle side? Not a thing. Okay. Now, what are we assuming here? Who wants to give it a shot? With a statement about, in context, what we're talking about, that you're assuming for this problem for independence. What are you assuming about independence? Somebody give it a shot. Somebody give it a shot. Somebody. Nobody. Anybody out there listening?
How do you say it?
That's what I'm asking you.
What do you mean by an assumption?
Like a statement that says you think that there's independence going on in this scenario. Everybody has their own reason. I don't really care about the reason. What do I care about? If they're speeding or not. So if I tell you the car that just went by me is speeding, will that affect the next one?
No.
So if you're saying no, then you're saying you think they're independent. That's what I'm asking for. Now, can anyone think of a scenario where that would not be true? Where you're on the high... Yeah, I'm sorry, Brisson. Absolutely. What if we went out to the freeway at 4:30 p.m.? Do you think that's going to affect whether people are speeding or not? Absolutely. You get on 288, and they've got construction for miles, for years. Okay, absolutely. Does that affect speeding? For sure. So traffic. So if we're going to do this, we should do this in a place that doesn't have construction, or do it not during the rush hour. Yes?
Whenever they're chasing us.
Ooh, a high-speed chase. That sounds exciting. Man, that'd be fun. Yes, would that be a problem? Absolutely. And so the police cruisers would be going really fast, chasing down the person. What about the cars that they're passing? Really slow, right? They're trying to get out of the way. Ah! Right? Don't hurt me. Great. That's a great example. There's one more I'm thinking of. Yeah, Edgar. Ooh, that's right. So an emergency vehicle, that wasn't the one I was thinking of, but I like it. The emergency vehicles, like fire trucks, ambulances. That sounds like all I know. Okay. Say it again. The bridge breaks? What is happening in your world, Susanna? Everyone has a reason for speeding. Now the bridges are falling down. The world is crumbling! Yeah, I don't know. Yes, obviously, if you're like, okay, how fast are they going? And then the bridge, yeah, you should worry about the people, not about your study. Yeah.
Or like the yellow light, something that's not make it short sensitive.
Okay, fair enough with the lights, but I'm talking about the freeway. So I'm assuming there's no lights on the freeway. Yeah, so I'm focusing on the freeway. I'm thinking of one more. Yeah. Juliana?
Like an accident.
An accident? I'd say like traffic accident. Oncoming traffic? Like you're going the wrong way?
No, like, I mean, like, you're coming,
Oh, like there's traffic on the other way?
you know, you're coming on the entrance drive and they're coming like pretty fast. You just have to slow down and speed up.
I see. Okay, so entering and exiting, merging, the feeder roads. Yeah,
Like, I don't know what this is
Whenever
called.
you're good.
there's an accident, people slow down, like.
Rubbernecking. When there's an accident, that's what it's called. When there's an accident, not like near you, but like on the other side, where people slow down. Like, oh man, look what happened! Ah! You get in your own accident. It's called rubbernecking because like your neck is whipping back and forth. No, that just gave me whiplash. Okay. I wasn't talking about the weather, but absolutely that would affect it, right? Especially here, if we get a light little freeze. Ah! Right? The road's crazy. What I was thinking of, have you guys ever been on the freeway and you get like a limo carrying a hearse, or it is a hearse carrying the coffin, and like the people with their flashers on following, right? They're usually got a police escort, and they're going about 50. They're going slower so everybody could stay in line. I was thinking about that one. It's a little morbid, but that's the one I was thinking about. Okay? Now, we just came up. I'm so proud of you guys. You just came up with at least 5 ways that we would violate the independence assumption. Did you hear that? You just came up with 5 different ways. Way to go. So how do you feel now? Do you still feel good?
Like, validate, like.
No, the opposite of validate. We just said, I just asked you guys if you thought that these were independent events. One car speeding doesn't affect the other. And you said, yeah, they're independent. But then we just came up with 5 ways that they wouldn't be independent. Traffic, rush hour, accidents, merging, emergency vehicles, police chase, whatever. So how do we feel now? We still feel good about this?
Yeah.
You see what I'm trying to say here? This is the hard thing about actually doing statistics work. You'll never feel confident in what you're doing. You're like, okay, I feel confident. No, now I don't. Wait, no, I feel confident again. That's called life, guys. All right? I know. You can only make decisions on the data you have. That's all you can do. And you go with it. And if it messes up, get better data. Okay. What can we check to make us feel better about this? What can we check to make us feel better about this? What conditions can we check to make us feel better? Let's start with the randomization condition.
So we don't put anything for the independent.
Do you remember that sentence that I just said? Like, I'm assuming that one car speeding will not affect another car?
That's right.
Yeah. I'm treating this like you're in college. So I'm recording this lesson if you want to listen to it again and write down notes after. But I don't have enough room to write all that out. But I would write, I am assuming one car's speed does not affect another.
Even if we just like came up with all those different.
I might write, if this was a test and I had time, I might write, I'm a little worried if it's like an emergency vehicle situation or they're doing this at rush hour or anything else you want to list. I might write that. All right, just to impress the teacher. Okay, so what are we saying about the randomization condition? What are we hoping that we saw or heard when Emmanuel read the sentence and the question? We're hoping that he read something that said what? We're hoping to see the word what? What word? Don't think so hard. We're hoping to see randomness, randomly. We want these to be random samples. So how would you get a random sample? By getting speeds of cars on the freeway. How would you get a random sample? Oh, wait every 10 seconds? There are no right answers here? There's no right answers? Whatever you got. Anyone else have a good idea? So you're like, okay, I'm going to do this car, got their number, 1, 2, and then you're going to wait and then do another one? Okay. Anybody see any problems with that? I think like logically or logistically that makes sense to me because you need time to, tell someone next to you how fast that car was going or write it down, make a note, right? If you're just going, you're not going to get, you're not going to get everybody's speed. I'm not a cop, but I don't think it's that easy. Ooh, the type of car. Should we be thinking about the type of car? And these are amazing questions. Do you think I know the answers? No, I don't. Sadly, did Emmanuel read anything that said they randomly selected these 50 cars? No. I'm hoping it did. But do I have any real worries that if I just tick any 50 cars on a freeway in Houston, that it wouldn't be random? You think I'd get a semi-truck in there? Probably. There's so many on there. Think I'd get like a Dodge Challenger, like a sports car? Yeah, I'll probably get one of those. Maybe I'll get a school bus. Who knows? Right? What I'm trying to say is I have no reason to believe that if they just took 50 cars from any of these freeways, that it wouldn't be random. So I'm okay with that. Even though I would have liked to see they randomly sampled. The other condition, the 10% condition. Now this one we can actually do a little bit of math here. What is our sample size? 50, right? They're going to sample 50 cars. That's not a negative sign. That's like a dash, like a bullet point. Sorry. So our sample size is 50 cars. Take that number and multiply it by 10. What do you get? 500. So ask yourself this question. Do you think there are more than 500 cars on the freeways of Houston?
Yes.
Yes. So our sample size is not too large. All right, I'll repeat that for those listening at home. We multiplied our sample size times 10. We said it was 500. Okay? As long as we think there are more cars on the freeway in the city of Houston, our population is more than 500, we're okay. 50 is not too large. Everybody good? Now, the reason I focus on that at the end, it's not too large, is because we're going to do the next assumption, which is called the sample size assumption. And that assumption says we think 50 is large enough. So we just checked and said it wasn't too large, right? Everybody good? That's what we just checked with the 10% condition. Not too large. But now we need to make sure that it is large enough. So that's the sample size assumption here. 50 is large enough. So what I just said there, Yesenia, is what I would write. My sample size of 50 cars is a large enough sample. My sample size of 50 cars is a large enough sample. That's what I'm assuming. Now, what can I check to make me feel good about that assumption? We checked this last week. Sad. What condition can I check? The success and failure condition. Because again, what I asked you at the very beginning, is anyone actually going out to the freeway to use a radar gun to get this data? No. So before we even do that, we can expect a certain number of cars to be speeding. So we're going to check N times P and N times Q, which seems similar because that's what we did last week. So our sample size is 50. What proportion of all vehicles on the Houston highways are speeding? 80%, so 0.8. That's my P. So then it's going to be 50 times how many are not speeding? 0.2. That's what the Q means. And that is similar to what we did in our last unit. And again, I guess you could think of it, a success in this scenario is speeding. All right, so what's 50 times 0.8? 40. And what's 50 times 0.2? 10. And you can always check these two numbers should add up to the sample size. Now, are both those numbers 10 or higher? Yes, one of them is exactly 10. So, woo, it was close. But we're saying that our sample size is large enough. So right here, sample size, not too large. Sample size, large enough. Not too large, large enough. Everybody see the difference? Yes, question. Well, what I would compare these numbers to is if Jalen said, hey, I'll go do this for you. I'll go walk along the side of I-45 and I'll measure 50 cars and bring back the data. All right? So before Jalen goes, I'm expecting him to find 40 that are speeding and 10 that are not. When he comes back with the data, will it be exactly 40 and 10? Could it be? Of course. Most likely, it won't. But that's what I expect him to find when he goes and does it. How do we feel? How do we feel? Feel good? We haven't actually done anything, but we have, right? That's the best thing about stats. We've done all this work, but we really haven't. No? Okay.
Can you tell us 40 large enough?
Hold on. All of this was still talking about 50.
Oh.
50 is the number I care about. I'm saying out of 50, I need to expect 10 or more successes and failures. So I'm sorry, I didn't make that clear. Thank you. All right, so we just need to check that we have enough successes and failures to make sure that this is large enough, the sample size. Good thought, my bad. I'll teach better next time. Okay, you guys ready? Let's actually do something. Let's draw. You should have a slide right underneath. I want you to draw that curve. So much pressure. Not the whole, I mean like, a good part of it. If you've already started, it's all good. Okay. I just drew, sorry, it doesn't look very good, my bad. I just drew the normal model curve. So that means I should be writing a capital N with what two parameters? Not P and Q. Mu. Let's start really generic. Mu and sigma, right? Winky alphates. Right? Now, you know that we're not going to use mu and sigma. What are we going to use for our mean or mu? What letter am I going to use? That's right. P. That's called the population proportion. Population is fun. You're going to love it. It's like alliteration. Population proportion. Right? That was an English word out there, by the way. I don't even like English. Right? Who needs English? I'm not going to go to England. Why would I need to learn English? Okay? So, no, it's from The Simpsons. Ever watch that show still? It's like a Homer in high school. No one knows The Simpsons at all? Oh my gosh. There's like an episode where he's in high school and he's like, I got English class. And then he's like, English? Who needs English? I'm never going to England. Oh, that was funny. Tough crowd. Okay. Now I kind of glossed over this during the notes, but I'm going to bring it back right now. This is sigma, which is standard deviation. The formula we're going to use is the square root of P times Q over N. You never need to memorize that. I will always give it to you. Kind of looks funny with one parenthesis being a different size, so I'm sorry. Okay, so let's find out those numbers. We already know what P is. What is P? 0.8. So before I even do anything, right in the center of my curve is going to be what? 0.8. Now, for the standard deviation, let's do a little work here. 0.8 is P. So what is Q? 0.2 divided by the sample size of 50. So we're going to take out your calculator to do the square root of a fraction. 0.8 times 0.2 divided by 50. Let's see. Oh man, Suzanne's going to beat me.
565.
Well, I mean, just didn't even give me a chance. 0.8 times, that's not 0.8, that's negative 8. 0.8 times 0.2 over, oh my gosh, over 50. 0.057. Do you round, yeah? Okay. Yeah. 0.057. I'm going to pause here. Any questions on how I find or how I found any of these numbers? We're almost there. Now, think back to chapter 6. Oh man, that was a long time ago. How many standard deviations do I care about when I look at a normal model? 3 in both directions. So go up 1, 2, 3, down 1, 2, 3. So right now, take your calculator and do 0.8 plus 0.057 and do it a couple of times. And then do it the other way as well, subtracting. All right, now I'm going to go the other way. Okay, I'm going to let you guys catch up. Because this is the moment where I need to kind of wrap everything into a nice little bow. All right, so I'm going to do my best here. This is why they pay me for this moment right here. Okay? You guys ready? All right. Here's what I'm saying. If you want to write this down, you can. I'm not going to force you to. Some of you have room to write down a sentence. It's a pretty long sentence. Some of you don't. You can write it to the side or underneath. According to the model. Would it be helpful if I typed it in? Yeah? Cool. Let's type it. Okay. According to the model. Well, you can't see that now, can you? There we go. According to the model, I expect 68% of my samples of 50 cars to have between 0.743 and 0.857 cars that are speeding. Anybody know the next number I'm going to use? I expect 68, then that does come after 68, but that's not it. 68, 95%. I expect 95% of my samples of 50 cars to have between 0.686 and 0.914 cars that are speeding. You know the last one? 68, 95. Very good, Juliana. 99.7%. 99.7% of my samples of 50 cars to have between 0.629 and 0.971 cars that are speeding. That was a great sentence. I guess sentences, to be exact. Good call. Okay, let's summarize real quick. I'm going to choose Jalen again because I chose Jalen the last one. Jalen is going to go out and do this. Thank you, Jalen, for volunteering. I appreciate you. So Jalen's going to do this. When he comes back and tells us his proportion, his p hat, because it's a sample, let's say Jalen comes back and tells us his p hat. Jalen tells us his p hat is 0.99. So he's telling us 99% of the cars he sampled were speeding. What would we think about Jalen's data? It would be unusual, Sylvester. Why?
More than the expected.
Well, we've moved on to other things here. It's more than it would be, right? His number of cars would be more than the expected value. But Sylvester, your brain is right. It's more than what? Oh, but more specific, how many standard deviations? Very good. It's more than 3. It's past 3 standard deviations from our expected mean of 0.8. All right. What if he came back and said his p hat was 0.7? So 70% of the cars he found were speeding. What would you say about his number? Okay, I love it, Sylvester, right? Does anybody have any issue with 0.7? It's between 1 and 2 standard deviations below. Cool. Nice work, Jalen. Glad you didn't die while you're out there. Good job. Right? So we're always looking to see if our actual samples that we go out and run end up being past these numbers here at the far left and the far right. That would be unusual. Yes?
How do we get the percentages?
How do we get the 3 to the above and 3 below?
68%.
Oh, this is that rule I taught you in, I think, October. That was for a normal model, 68% of the data will fall between 1 standard deviation above and below. So like here to here is 68% of the data. And then if you go another one on either side is 95%. So pretty much all of our data is between 3 above and 3 below. That's why we say if somebody finds anything that's past our last numbers in either direction, it's unusual. That's what we're saying. All right. So I'm going to pause here. Jalen, I'm coming back to you for our outro. You ready?
Bye.
All right. Thanks, Jalen. We out.